CLC schedule is posted. I expect you know that CLC is Chemistry Learning Center, which is the name given to the area where our discussion instructors meet their office time to provide you the opportunity for out-of-class assistance. Flint 257. So if you look on Sakai, our website for the class, you can find this schedule. Back to introductory considerations regarding equilibrium. Yesterday in discussion class, you began with some considerations which will allow us to tackle and analyze equilibrium systems regarding Bronsted-Lowry acid-base chemistry. We'll proceed with that after we finish Chapter 17. I have chosen to finish Chapter 17 in class rather than have the folks finish with it yesterday in discussion class because we need some demonstration stuff, and that's not easy to get at in discussion class. First, regarding equilibrium or the possibility of the existence of equilibrium, we've looked at 5 systems. The system produced by saturating air above water in a stoppered flask. And for that we talked about how to evaluate the equilibrium constant, either in terms of concentration or partial pressure. Then we looked at some calcium chloride solution, recognized by observation that after we dissolved the calcium chloride, there was no solid remaining. Conclusion, no equilibrium involving solute because all the calcium chloride we added dissolved. To establish equilibrium between calcium chloride and its component ions, calcium ion and chloride ion, we'd have to continue to add calcium chloride to the system while stirring to speed up dissolving until undissolved solid remained. We didn't do that. Then we talked about 1 molar hydrochloric acid solution. Recognize that in preparing that solution, all the HCl used to make the solution reacted with water to make hydronium ion and chloride ion. So again, no equilibrium involving solute because all the added HCl converted to hydronium ion and chloride ion respectively. That led us to our first look at principal species inventory. Point: if you are going to do chemistry with a chemical system, you have to know what's in the system. It's impossible to do chemistry on a system and understand it if you don't know what's in the system. So for 1 molar hydrochloric acid solution, hydronium ion at a concentration of 1 molar, chloride ion at a concentration of 1 molar, water to solvent at a very high concentration, something on the order of 53 molar, and HClAQ, phooey. That's textbook nonsense. There are no detectable HCl molecules remaining in that solution after it is prepared. Then we looked at 1 molar acetic acid solution. Recognized that the ionization reaction of acetic acid molecules with water, producing hydronium ion and acetate ion respectively, only goes about 0.4% from a molarity of 1 for acetic acid solute. So, since all the solute did not convert to products, now we looked at a system involving equilibrium with solute acetic acid. We wrote the equilibrium constant expression and talked about how we could get a handle on the molar concentration of water in that system. The remaining system, which we've not yet discussed in detail, is this one. calcium carbonate saturated water solution. Here again is that system. On the bottom of the pot, we see the calcium carbonate undissolved. If I shake it up, the calcium carbonate solid will again distribute itself throughout the liquid part of the mix, and you will reobserve it distributed through the system. What I'm going to do, since we already prepared this system, is carefully transfer some of the liquid part of this system to a new flask and treat some of this calcium carbonate solution, because that's what we have here. Because we prepared this system by shaking water with calcium carbonate. I'm going to treat this water solution of calcium carbonate with phenolphthalein. You familiar with the behavior of phenolphthalein? Phenolphthalein, a very common acid-base indicator. Just for curiosity's sake, in high school chemistry, how many of you did some work with phenolphthalein indicator? Oh, that's good. Did you learn that at a pH slightly above 9, it's actually about 9.2, a phenolphthalein treated solution which is previously colored, on having the pH raised to about a value of 9.2 or greater, will then begin to develop a red-pink color. What does that tell you? This pH greater than 9.2. What's that really telling you about the chemistry of the system?
Concentration of hydronium ions.
What is this pH greater than 9.2 telling you? You see this red-pink color with phenolphthalein. What do you know, chemistry-wise, from that observation?
A higher concentration of hydroxide ions than in pure water.
You now have a system which is said to be basic, because it contains a hydroxide ion concentration which exceeds that of hydronium ion, and by a rather substantial amount, ratio-wise. You can verify that with some pH arithmetic. So I put in a few drops of the phenolphthalein indicator. Can you observe? It's not particularly intense, but can you observe a distinct red-pink color in here? So, what we realized is that on dissolving calcium carbonate in water, something happens above and beyond just putting calcium ions and carbonate ions in solution. Because, as was just pointed out, when phenolphthalein treated water solutions show this red-pink color, we have a solution that's basic. And basic means that the hydroxide ion molarity is greater than the hydronium ion molarity, which in turn means when calcium carbonate was dissolved in water, hydroxide ion had to be produced. So, I wrote on the board two equilibrium statements. This equilibrium reaction, which shows the establishment of equilibrium between solute calcium carbonate in water solvent with its component ions, calcium ion and carbonate ion. This equilibrium reaction is correct. It does correspond to saturating water with calcium carbonate. But this equilibrium reaction does not show the chemistry which we just discussed. So I've written this reaction. Calcium carbonate plus water. Does it seem that it must be true that since the system became basic, since the dissolving of calcium carbonate made hydroxide ion, a reaction between calcium carbonate and water had to happen? If nothing else, calcium carbonate doesn't have any hydrogen in it. It can't possibly convert to hydroxide ion. So I also wrote this equilibrium reaction. We're showing equilibrium between solute on reaction with water to make calcium ion bicarb ion and hydroxide ion. Now, we're not going to go further with this equilibrium system, nor this equilibrium system at this stage of the game. But when we get into chapter 19, we're going to look at these equilibrium systems in detail. You will see how to analyze these systems completely so as to do things like calculate the pH, calculate the hydroxide ion concentration for water saturated with calcium carbonate. But I would ask, and you were introduced to this stuff in 45 laboratory. You were introduced to this stuff yesterday with discussion class consideration. See these formulas? You won't find these formulas in textbooks. What's this the formula for? What is it? Bicarbonate ion, or more chemically wise, hydrogen carbonate ion. In textbooks, how have you seen this formula written? HCO3 minus. I'll write that over here. We have reminded ourselves the most important property by far of a species is its structure. If I give you this formula, if I give you the textbook formula, and I direct you to write a Lewis structure for this thing, you're trying to get at its structure. What are you going to write? If I give you this formula, you've all seen this formula. Sulfuric acid molecule. I tell you to write me a Lewis structure for this stuff. Most important property of this stuff. What are you going to write? Are you going to write a formula here which shows hydrogen atoms bound to sulfur? You'd be wrong. You're going to write a Lewis structure which shows hydrogen bound to carbon? You're wrong again. So I try to make a practice of writing formulas as well or as best as I can to correspond to structure. Because when I write the hydrogen carbonate ion formula like this, I'm telling you that hydrogen is covalently connected to oxygen, which in turn is covalently connected to carbon. There's no hydrogen-carbon bonds in this thing. Hydroxide ion. I can't believe textbooks that write OH minus. I really can't believe that. From a fundamental standpoint, that's about as stupid as anything could be. You did this in discussion class, but it's important, so I'll do it again. When I convert the water molecule to hydroxide ion, I do so by breaking off H as H+. That means I can break either one of these bonds, because they're identical, heterolytically with the electron pair that previously was a bonding electron pair winding up exclusively in the valence environment of oxygen. Or it doesn't make any difference. If I now calculate formal charge, which you should do every time you write a Lewis structure, you find out that the negative charge is on oxygen, not on hydrogen. Would you expect that based on electronegativity? Absolutely. You'd expect to break this bond so that the previously bonding electron pair winds up in the valence environment of oxygen rather than hydrogen, because oxygen is much more electronegative than hydrogen. So, I write the formula for the hydroxide ion like this, which keeps with the convention of writing the formula for the more electropositive atom first. And notice how it corresponds, this formula, to its name. Hydroxide ion. What? This damn mess. So just the negative charges on hydrogen, and this would be oxyhydride ion. What the hell is that? It doesn't exist. So I don't do that stuff. And when my fellow instructors tell me that I'm going to cause confusion with this, I say, no, you're the one causing the confusion. Because the most important property of these damn things is structure, and this belies structure. This belies chemical properties of this entirely. So what the hell are you teaching in here? Aesop's fables? Or chemistry? If you want the Aesop's fables, you can keep with this traditional and totally incorrect formula for hydroxide ion. And then you can take my exams and flunk. How's that for an attitude? Now then, a practical demonstration of equilibrium. I have before you two cylinders, same size, stoppered. Cylinder A contains 200 milliliters of water in which I have dissolved 0.2 of a gram of potassium iodide. Florence flask A contains 200 milliliters of toluene in which I have dissolved about 1/10 of a gram of iodine. Cylinder B contains 200 milliliters of water plus 0.2 of a gram of dissolved potassium iodide plus 1/10 of a gram of dissolved iodine. Florence flask B contains 200 milliliters of toluene. Therefore, when I put the contents of flask A into cylinder A and the contents of flask B into cylinder B, I will have identical systems compositionally. Since these systems are identical compositionally, and since water and toluene are immiscible liquids, remember what that means?
When does it dissolve?
Do you remember dealing with miscible versus immiscible liquids in assignment 7 and 45 laboratory last term? Do you remember, for example, in that experiment mixing up water with hexane? Remember mixing up water with methylene chloride? I'm just curious if you remember doing those things. Since these liquids are not miscible, miscible means regardless of the volumes I use for each liquid, when I put them together and stir, I will always get simply and exclusively a true solution, never an interface. Immiscible means that even though when I shake toluene with water, some of the toluene dissolves in the water while some of the water dissolves in toluene, I'm going to get an interface.
An inter what?
Pardon?
An interface?
Interface, a separation. You'll see the interface when I make this mixture. Okay? Now, since these systems are of identical composition, and since I will have an interface right here, notice as soon as I added the toluene solution containing the dissolved iodine, that system is less dense than water. That's why I started with the water part of the system in the cylinder first. You see the color beginning to develop in the lower deionized water phase? See the little bit of yellow-brown coloration developing? Color-wise, what am I going to see when I now add the pure toluene? I can get the stopper out. Toluene swells rubber. I made these with the intention of doing this a lecture ago, but I didn't get to it. That's okay. What are we going to see when you add the toluene now to the system which already contains the I2 in the water layer? You see the color beginning to develop in the toluene top layer? Now then, back to Chemistry 2045. Back to 2045 Laboratory Assignment 7. Here, well, before we do that chemistry, here's why I put the potassium iodide in there. I2, as I expect you learned in Assignment 745 Laboratory, as I expect you learned in 2045 lecture class, I2 is not very soluble in water. Why not?
It's not cool.
Well, you tell me nonpolar. Can you tell me more than that?
The two iodine, or the two iodine atoms in the molecule share the electrons evenly.
Well, that's true. That's why I2 is not polar.
Because they're both iodine atoms, they have the same electronegativity.
Well, that's why I2 is not polar.
The outer valence electron shells are totally full.
Well, okay. But I want to know why this nonpolar stuff, in this case I2, does not dissolve effectively in the water molecule, in the water stuff.
It's because water's polar and iodine is nonpolar.
That's true, but tell me more. What does this polar, nonpolar stuff mean?
In solutions, the polar solutions mixed with polar solutions, nonpolar solutions mixed with nonpolar.
Well, what does the word polar mean?
That there's an electronegativity inside that atom. That one molecule in that atom is polar.
When two things are polar, when something is polar, it means that its particles, or its molecules, one side is positive and one is negative, so when you mix polar things, the magnetic forces will cause them to...
Magnetic forces.
Iodine molecules cannot form hydrogen bonds with water molecules.
Well, that's true, but many materials don't form hydrogen bonds with water molecules, yet they're quite soluble in water. Like sodium chloride.
Because there's unequal sharing between the polar molecule.
Unequal sharing of what?
The two atoms are unequally sharing. One atom is getting more of the electron in its shell than the other.
And even the distribution of charge in the water molecules will cause them to attract each other more than they'll attract the iodine.
Okay, you're getting there. What I'm curious about is how many of you recognize that these terms polar and nonpolar each describe the electrical nature of the particle. Did you learn that? Water molecule. Above the oxygen atom, I'll write squiggle minus. Squiggle means partial. Because the oxygen atom, which is of considerably greater electronegativity than hydrogen atoms, and with the oxygen atom having non-bonding electron density on it, the oxygen atom is partially minus with respect to the hydrogen atoms, which are partially plus with respect to the oxygen atoms. However, for the I2 molecule, the valence electron density is perfectly symmetrical. It's distributed in a perfectly symmetrical fashion for this molecule along the bond axis. If you could see an I2 molecule, what would it look like? If you could see an I2 molecule, what would it look like? What would it look like? Would it look like a stick with two symbol eyes connected to each other? It would look like that, wouldn't it? What would it look like?
A lot like a bromine molecule.
What does that look like?
It's two nuclei with...
What do nuclei look like? I want you to tell me what this thing looks like. What?
It's like if you took two circles and then you merged them.
Circles, these things are not flat.
Spheres.
Spheres, we're going to merge spheres, okay.
Merge them, so it's kind of like a cucumber shape.
A cucumber shape, good. That's not bad. I prefer egg.
Okay.
Look like an egg. Maybe like a short cigar. Okay? We're trying to be as practical about this as we can be. The point is, these two molecules are very dissimilar electrically. These molecules electrically are much happy in contact with each other than they are in contact with this thing. Because this thing doesn't have any non-uniform electron density distribution. This doesn't have any partial squiggles. This doesn't have any squiggle minuses and squiggle pluses. Doesn't have any partial charge character. But this does. Now then, here's toluene.
Okay, we try and get this straight. Toluene is immiscible with water.
I didn't hear you.
Toluene is immiscible.
Toluene and water are immiscible liquids.
And then I2 is immiscible with either of them?
Oh no. The I2 is dissolved.
Yeah, but you guys said
Immiscible applies to liquids. I2 is not a liquid.
It's
Solid. Yeah. Let's look at this picture. Did you see any pictures like this in 2045? What does this part of the picture correspond to? Represent? What is this? What is that? It's a benzene ring. So toluene is a benzene ring to which a methyl group is attached to one of the carbons. Doesn't make any difference because on the benzene ring all the carbon atoms are identical. Okay? Tell me something about the polarity of toluene. Tell me why I2 is much more soluble in toluene than it is in water. They're much more electrically similar. So that tells you something about the polarity of toluene. How polar is this molecule? You think this molecule is slightly polar? Because it's got his methyl group up here, which corresponds to an electron density region which is somewhat dissimilar from the electron density regions of the carbons and the hydrogens that are connected to the carbons that are part of the ring. So this thing is slightly polar. But the water molecule is not only significantly polar, it's hydrogen bonding. So that provides an account of why I2 is much more soluble in toluene than it is in water. Okay? Notice, if you will, just as we talked, here, not much color has transferred to the water layer, keeping with the fact that I2 is much more soluble than toluene. Now again, I've purposely laced the water with potassium iodide so that by this reaction, we can get some of the I2 to dissolve into the water layer and make the I2 dissolved in the water layer observable. Because if the color is so faint, the yellow-brown color is so faint of the dissolved I2 in water, then you say, well, I'm not seeing any I2 in the water. Okay. So this reaction occurs. It's an interesting reaction. It comes in a category of reactions known as Lewis acid, Lewis base, which we'll also begin to talk about in detail in Chapter 19, to form the triiodide ion. Did any of you talk about the triiodide ion in 2045? If you write the Lewis picture for the triiodide ion, what kind of shape will you get? What kind of central iodine atom hybridization will you get?
I can't answer hybridization, but doesn't it have that extra, essentially an extra electron plus?
I want to know what the shape of the species is.
Understood.
Okay?
Trigonal planar. Is it trigonal planar? That's just a guess.
Trigonal planar.
It's not in my head.
It's impossible to be trigonal planar. You got to have at least 4 atoms to define a trigonal plane. 1 in the center and 3 surrounding.
Okay.
What's the shape of this I3 minus?
I'm gonna guess bent.
You guessed wrong. But you guessed.
Linear?
Linear. It's not bent, it has to be linear. It's linear. All right, I give you an assignment. You write the Lewis picture for that thing and determine hybridization for the central iodine atom. Would you believe the central atom is iodine? All right, we proceed to equilibrium. We recognize these systems, which I have constructed, are of identical composition. From that, we can answer the question, are these systems in equilibrium? They're of identical composition. Are these systems at equilibrium?
No.
Yes or no? How many vote yes? How many vote no? How many didn't vote? Non-voters? This Friday, in preparation for Labor Day weekend, non-voters will buy the beer and the pizza for our party. And the rest of us will feast off the non-voters. They pay because they didn't participate. All right? These systems cannot be in equilibrium, at least not both of them, because they're of identical composition, which guarantees that if they were at equilibrium, how would they compare? How would they compare? They'd look exactly alike, wouldn't they? All right? What can we do to get these systems to come to equilibrium in a rapid fashion? Why does shaking get this done? Do you realize that in this flask, where we started with all the I2 up top, the only way we can get I2 molecules to transfer to the bottom water layer is through this interface. Same for this flask, where we started with all the I2 in the bottom water layer. The only way I2 molecules can get to the top toluene layer is transferred through this interface. What do we do by shaking? You increase the magnitude of the interface big time. So I'll have some fun. Good exercise. Part of my weight loss project. My sweet wife says, that's okay. I like you eat a lot. Her stuff that she cooks, I eat a lot. Vietnamese food is great. This causes my camera person to have a fit because I'm jumping around. How about that? Equilibrium. Do you think, had we allowed the flask to stand without this agitation that I just performed, that they would come to equilibrium? How long do you think it'll take? How long is a long time?
2 months and 4 weeks. I think we come back on Monday, come back Tuesday.
When I first saw this demonstration done as part of teaching students about equilibrium, the lecturer purposely made 2 additional flasks, like what we had without the shaking, and put them in a locked demonstration case. That was at the start of the term. At the end of the term, they weren't anywhere near equilibrium. I'll put these here just to have them out of sight. All right? Now let's have some fun with regard to analyzing this system. Experiments indicate that the concentration ratio of I2 in toluene to I2 in water for the system we just prepared, provided I didn't put the potassium iodide in there, so forget the potassium iodide for this analysis. Because establishing equilibrium shows clearly, I think, the bulk of the I2 is up top. If I didn't have the potassium iodide in the bottom layer, it would be at best a very faint yellow-brown color. Again, I put the Ki in there to make the water layer more observable. All right? Again, experiments and measurements show that the concentration ratio of I2 dissolved in toluene to that dissolved in water is 70, keeping with the fact that I2 is much more soluble in toluene. Now, before we proceed with this analysis, I used to do this demonstration with carbon tetrachloride, but then the EPA decided that carbon tetrachloride is a carcinogenic material, so that we don't use that anymore. That's understandable. And if I used carbon tetrachloride, I would have had the carbon tetrachloride in the cylinders first, because carbon tetrachloride is more dense than water. Question is, if I use carbon tetrachloride for this demonstration instead of toluene, this concentration ratio, which is an equilibrium distribution constant because it represents the distribution of solute iodine into the toluene layer versus the water layer. If I use carbon tetrachloride instead of toluene, would this number be bigger, smaller, or the same? How many vote the same? That's good. Carbon tetrachloride is clearly a different molecule than toluene, so the same is not a likely bet. How many vote that with carbon tetrachloride as solvent for I2 rather than toluene, this number would be bigger? That's correct. Why would it be bigger?
Because it's less polar than, we established that the toluene is slightly polar.
Toluene. How polar is carbon tetrachloride?
Not at all.
Not at all. It's a perfectly symmetrical tetrahedral molecule. Consequence, the value is 80 if I use carbon tet.
I was going to say, carbon tetrachloride is a much larger molecule than I2, so it's going to be hitting the water molecules a lot more, so it's going to dissolve a lot more.
Remember, what we're talking about is electric nature with this polar non-polar stuff. The carbon tetrachloride is even less electric than toluene. Toluene is slightly polar. Carbon tetrachloride not polar at all. Now then, imagine, or how much did I say in the notes? Question 17.9 says 0.500 grams. Consider Consider or imagine that I had used 0.5 grams of I2 in doing this demonstration. But as opposed to the demonstration which we actually did, imagine we use 900 milliliters of water and 100 milliliters of toluene. For the demonstration we did, the volumes of the liquids were identical, each 200 milliliters. If I do this, instead of equal volumes of the immiscible liquids, water and toluene, if I do this, is it the case that the bulk of the I2, when we get to equilibrium, will now be dissolved in the water because the water layer is 9 times volume-wise greater than the toluene layer? Would the bulk of the I2 not now be found in the water layer? Yes or no? The jury's at odds with each other. You see that number? Among other things, this number means that if I want to distribute I2 between a mix of toluene and water, and I want most of the I2 to wind up in water, the volume ratio of water to toluene, the volume ratio of water to toluene has got to be bigger than 70 to 1. This means that. Okay? So even if I do this, the bulk of the I2 is still going to be in the toluene layer. Because 9 to 1 is hardly 70 to 1. All right? Now how do we do the calculation? Well, we'll start with some algebra. I'll represent the mass of I2, which at equilibrium is to be found in the water layer, as X. If I do that, algebraically, what will be the mass of I2 dissolved in the toluene layer? I will tell you that I once saw a chemistry lecture tackle this very same problem and represented the mass of I2 in the toluene layer as Y. X for the mass of I2 in the water layer, Y is the mass of I2 in the toluene layer. And then in short order fashion became very beet red before the class, because he now recognized that he can write one equation which will contain two unknowns. And you can't solve that. So what's the correct way to define algebraically the mass of I2 in the toluene layer? This. All right? Now, what setup do we write to solve this puzzle? Realize that this is a ratio of concentrations. I have masses of I2. Molar concentrations related to masses. You learn in 2045, if for any chemical substance you want to relate moles to mass or mass to moles, what property of the substance must you use? Molar mass. Formula mass, molar mass, same thing. So, I'm going to get out my periodic table, the one that's in the notes, not this one, if I want molar mass for I2, and I'll write 1 mole I2 per FM for formula mass I2 times 0.500 grams minus X, because the unit on this is grams, the unit on this is grams, and I want molar concentration. So what do I write here to get this term to give me molar concentration of I2 in toluene? What do I write here? I write this. And now I go to the bottom and I write 1 mole I2 over formula mass I2 times X over 0.900 liters, and I discover I don't even need the molar mass of I2 to do this arithmetic. Simple. First order equation, I solve it, and I get something. There it is. Showing us, as we recognized before we did this problem, that the bulk of the I2 will still wind up in the toluene layer. And not thinking you should always do before you start grinding at arithmetic. Because if you do this arithmetic, and you wind up with a calculated mass of I2 for the water layer that exceeds the mass of I2 in the toluene layer, you did something wrong. Now, in preparation for our next talk, I want you to look at challenge problem 17.1 at the tail end of chapter 17. Carefully, because we're going to look at that in detail to wrap up chapter 17, and then we springboard back into chapter 18 and continue with such.